Good afternoon. My name is Gurjinder Singh, and I'm a research scholar at Lovely Professional University. My research mainly focuses on developing high performance coating for extreme environment conditions. And my topic is hot corrosion performance of plasma sprayed in Cornell, which is basically a nickel-based superalloy plus yttria stabilized zirconia composite coatings. Coming to introduction, uh, in introduction, there are some challenges of high temperature. As in our mechanical engineering industry line, some critical component in our industry, like in our gas turbines, in marine engine, and in aerospace engineering, some component operate in very extreme harsh conditions and environment because those components are subjected to high temperature mechanical stresses, which in result when which in result you can say the combination of high temperature and mechanical stresses can limit the lifespan of the components of the mechanical engineering industry line. And basically, due to our environment condition, there are some molten salt formation. And those molten salts are mainly sodium sulfate, Na2SO4, and vanadium oxide, V2O5. And these molten salt have a major effect on our material life. And now, what is the root problem of these corrosion? Now, many companies to reduce the operational cost often tries less expensive and you can say low grade residual fluid fuels which may contain some contaminants like sodium, sulfur, and vanadium, and these contaminants result in our main corrodant that are molten salt, sodium sulfate, and vanadium pentoxide. And these molten salt result in our removing the protective material coating. And this is the literature review which I have downloaded. These are 50, almost 50 papers, and this is the screenshot of my PDF downloads. And this is the bibliometric analysis I have done with our literature review. Now, coming back to our topic. So, first we need to understand what is hot corrosion. So, hot corrosion, it is not a simple oxidation. It is a accelerated degradation which mainly driven by the molten salt as I have discussed earlier. Now, how it works? Now, all in when we say in industry lines, the traditional inconel coating is done on our material because it is a superalloy, it is a nickel-based superalloy, and it offer excellent high temperature strength and corrosion resistance. But there is some limitation of inconel. Long-term exposure to molten salt can lead to removal of the protective layer that is inconel, and that process is called fluxing. And with the protective layer gone, the base metal will get consumed by molten salt and high temperature gases. Now, hot corrosion mainly is of two types, type 1 and type 2. Type 1 is basically when corrosion is done at high temperature. The temperature range is 800 to 950 degrees Celsius, and type 2 is low temperature. Low temperature range is 700 to 750 degrees centigrade. And salt state in type 1, The main alkali metal salt are sodium sulfate Na2SO4, which act as a flux. And in type 2, there is a mixture of sodium sulfate and MSO4. M may be other metal like nickel or cobalt. What is the corrosion mechanism of both types? In type 1, molten salt basically dissolve the protective oxide scale, as I have discussed earlier in our previous slide, that is molten salt dissolve the inconel layer. And in type 2, it apply pressure to stabilize the mixture, and that pressure attacks the metal. What are the failure modes? In type 1, mainly sulfur penetrates the scale, which result in internal molten sulfide, for example, nickel sulfide, which destroy the material. And in type 2, there are the acidic liquid, which dissolve the protective oxide scale, or you can say layer, which leads to localized pitting. That is, there are pits on the surface. Now, what are the objectives of research? In our research, I am planning to study a well-known ceramic metal, that is yttria stabilized zirconia, which has a high thermal stability, low thermal conductivity, and a good corrosion resistance. But I am not planning to simply coat the wire stud on the material. We used YSZ in combination with Inconel as a composite coating. And we are planning to do that coating via plasma spraying technique. Why plasma spraying technique? Because it offers potential improvement in hot corrosion resistance by acting as a thermal chemical barrier. Now, what are the research problems? So there are some research gap, or you can say knowledge gap exist in our work. What are the formation and stability of a protective oxide scale after coating? And if we are mixing the Inconel and YSZ, what are the interaction between Inconel and YSZ faced during corrosion? And what are the influence of coating on corrosion performance? Now there are some limitation of both material Inconel and YSZ. Due to that limitation only, they cannot be, you can say, effectable when used alone. So what are the different limitation? So nickel Bose superalloy, that is Inconel, they are traditionally used, so you can say it are the structural backbone of a hot section component. It offer excellent high temperature mechanical strength, but the critical flaws are their only corrosive defense is protective oxide scale they form, which get degraded by molten salt. And to conclude, Inconel alone is insufficient for long-term survival in an environment contaminated with Na2SO4 and B2O5. And what are the limitation of YSZ alone? It is the industry standard material for thermal barrier coating, YSZ. So function is, it acts as a ceramic top coat that acts as an insulator, lowering the temperature of the metal component. What are the limitation of this when you use alone YSZ? It is not corroded like a metal, but due to mechanical stress, it may develop cracks. And it is also chemically, it can be also chemically attacked by B2O5 in the molten salt. So our research gap shows if we use only thermal barrier coating with YSZ, 100% YSZ or 100% metallic bond coat. And what are the unknown? That is, what are the gap? The hot corrosion behavior of this component architecture is not thoroughly understood. In this system, molten salt will attack both the Inconel and YSZ phase simultaneously. And we are planning to investigate our project in the composition of YSZ and Inconel. First, we are going to mix the Inconel and YSZ in the composition of 70:30. That is 70 is Inconel and 30 is YSZ. Then 50:50, then 30:70. These are the hypotheses that we are formulate. First is null hypothesis. The Inconel YSZ composite ratio is no significant on the overall hot corrosion resistance compared to pure Inconel coating. When we compared to pure Inconel coating with our coating that is Inconel and YSZ composite, there is no significant effect on the overall hot corrosion resistance. And what is the alternate hypothesis? That there will be a significant effect on the hot corrosion resistance when we use our composite coating compared to pure Inconel. And what are the other null hypotheses? Changing the structure and composition of YSZ coatings do not affect the resistance to crack or damage during repeated heating and cooling. As I discussed earlier, there is limitation of YSZ that when they used only YSZ, the YSZ material may result in cracks due to mechanical stress. And if we are using the composition of YSZ and Inconel, that is composite material, there is no resistance to cracks. That is null hypothesis. And there is a significantly improvement in crack resistance with the use of composite. Now, what are the methodologies? That is fabrication. First techniques we are planning to use is atmospheric plasma spray, which is the very SOTA standard for this work, because in this process, we use approximately 15,000 Kelvin plasma jet to melt and deposit any material, including metal and ceramic, with vastly different melting points. So what is the process? First, we mixed powder Inconel and YSZ powder, and then we inject into the plasma jet. Then in plasma jet, the particles will melt and then propelled at a high velocity, that is 300 to 600 meter per second. Then after propelled, the molten droplet will occur splat on the substrate, rapidly solidifying to build the coating, which result in complete coating. So what are the experimental variables? Substrates are Inconel 625 or 718 or SS316, that is stainless steel. And what are the powder ratio? Again, I have discussed earlier, 70:30, 50:50, and 30:70. Second methodology are microstructure and porosity test. For microstructure test, we are using SEM analysis, XRD for phase composition, and for adhesion strength, we are planning to using adhesion pull test, hot corrosion testing. In this, we will test our material in both temperature condition, that is type 1 and type 2. Characterization techniques for microstructure SEM, optical microscopy, for phase composition XRD, for surface topography and roughness 3D profilometry, for porosity and hardness image analysis and micro hardness testing, for adhesion strength pull-off test. What are the expected outcomes? So we are, after our research, there will be a development and you can say development of a new material, composite Inconel plus YSZ coating with a superior resistance to V2O5 rich hot corrosion. And what our scientific insight? It is the first mechanistic understanding of the compositive corrosion and collaboration within the composite system. Optimized design. A clear structure property correlation that answer what is the optimal inconel Weisstedt ratio for maximum component life. So after research, we will be able to understand that what is the correct composition ratio to achieve the maximum corrosion resistance. And of course, we will be publication. We will do publication, and it will be high impact publication. Now, what are the significance and broader impact? We can use it as a direct industrial application. For example, we will apply it to gas turbine, diesel engine, chemical plant, and fuel flexibility. When we use a successful coating material, it would allow us to operate to use cheaper, lower grade fuel, which in the result enhance our income. Economic impact. It will extend service life. It will also reduce maintenance cost. It will also improve reliability. Now, what are the problems? What corrosion from dirty fuel is a critical multi-billion-dollar industrial problem. Every year, many money lost to maintain the materials which get corroded from hot corrosion. The limits. Existing materials, that is when existing coating is doing with Inconel only, or you, and when you talk about layered coating, that is using YSZ only. We are planning to mix the both, and that will result in well-defined failure mechanism. What are the novel approach? Then investigate. This research investigate a composite Inconel plus YSZ architecture, addressing a key gap in the literature. This is the Gantt chart for our full PhD work. These are the references. Thank you.